Hello. Good evening, everyone. Please anyone confirm, am I audible or not?
Yes, we can hear you.
Okay, thanks. Thanks for this. So, I think this will start. We are already late. So this, as you know, this session is for a revision session of the end term, and in this session we will gonna cover. We are gonna cover week 9, 10, 11, and 12. We will revise those, and initial weeks, week 1 to 8, is already been revised for the quizzes. So you can go to those sessions if you need revision for that. Okay. So these four sessions weren't, were not revised before. So we are gonna do that now. So shall we start? Yeah. One thing before starting. So the pattern is gonna be similar, kind of as per the last term. I mean, so there you can expect 2 to 3 questions from every week. So yeah. So if there are so if week is not that lengthy, then you can assume some less questions. Otherwise, you can expect 2 to 3 questions from each week. Okay. So some questions may be conceptual based, simple, just read the questions, use your concepts and just tick the answers. And some questions may be numerical kind of question where you have to update the weights, but that computations will be easy, right? Just additions or multiplication kind of thing, but you need not to worry about the lengthy calculations. Just go through your concepts and just do the manipulations, kind of matrix addition, vector additions and vector multiplication and all. Okay, so this kind of questions you can expect. So I think now we should start.
Yes, sir.
Okay. Okay. So can you see my screen?
Yes.
Okay, so we'll start with week 9. Okay, so week 9 is all about the decision tree. Okay, so we will not waste much time on the introductions. We will try to cover the basic ideas, the main ideas here, so that we can cover all the 4 weeks in this time. Okay, so decision tree what is decision tree? As you know, this is supervised learning problem because it is in every examples you have associated label with the every examples, right? So this is supervised learning algorithm. Second, it is non-parametric. So what do I mean by non-parametric? It means that we don't make any assumption about the distribution of the training data set, right? So that's, in that sense, it's non-parametric. We make no assumption about the distribution of the data set. Okay, so that's why this is non-parametric one. So this is one of the main advantage of the decision trees, because we don't we don't worry about anything, any distributions kind of thing here. So any decision tree can learn any kind of distributions in even very uneven distribution. Decision tree can learn very well. Okay, so that is the one of the advantage of decision tree, but it may be a disadvantage as well. But why will I'm saying that I'll cover in the last part of this week 9. Okay, and one more advantage of this, it can learn both. It can be used for both regression and classification techniques. Okay, so let's see what is this. So what are actually decision trees? Okay, so decision tree is nothing but it's in decision tree we actually divides our inputs into different parts. Okay, so let's assume you have a classification problem with the 2 features. Okay, so you have x1 feature and x2 feature, right? So since you have 2 features, your input space is gonna be 2-dimensional, and let's say your data set is distributed something like that. These are your one class examples, and let's assume some different. Let's say these are your another classes examples. Okay, and let's assume this is 3-class classification problem. One more class we can assume some different. Let's say this green color. Okay, so you have very simple example here. but you have two-dimensional input space because there are only two features. So how decision trees works here, we try to split our or divides our input space into different parts. Okay, so and we fit the model into those parts, fit our model into those parts, right? So how you will split, let's say this is your entire data set, and now how you will split, you can here see that if I split my data set using the feature x2 and such that if x2 is less than theta 1, let's say some value theta 1, then we are into this region. Okay, and if it is greater than theta 1, then we are into this upper region. So if greater than theta 1, and we are splitting according to x2, right? So we come into this region, and if it is less than or equal to theta 1, we are into lower region, right? Similarly, we can split these nodes again. If you look at the right node here, so right node we need not to split because here all the examples belong to the same class. Okay, so we can make predictions in this region, right? So what we do is split our region into different parts and then fit our model into those parts. Because now this part we can easily make predictions because we know in this part all the examples belong to the this blue points. Okay, so we can make a model, we can predict here. Similarly, we can use for this node. If you can see here, there are two classes. So we can split according to feature x1. So that if x1 is less than some value theta 2, we are into this left region, and if it is greater than theta 2, then we are on the into right region. Okay, so we can split into according to x1. We are into x left region, then we can make prediction that, and if we are in the right region, then we can make prediction as the green, right? So this is how a typical decision tree looks like. Okay, so this is what I mean by decision tree. Now, so this idea should be clear. Now, the main problem comes in how to build a decision tree, right? Okay, so some terminologies which are used for the decision tree. One is, let's say this is your one typical decision tree. Here you have node, entire data set, then you have split it into this part, and then you have split this part as this thing. Okay, and again this you have split according to something using some features. Okay, and some decision. Now the root node is the node which contains all the data, all the training data set. So this is called your root node, and all leaves nodes are what, where you make the predictions. So here the nodes which are used for making predictions. So all these nodes, the terminal nodes or the leaf nodes. So these are called your leaves nodes. Okay. And what are the decision nodes? Where you the nodes which you in which you split your data set or you make the decisions to split. Okay, so these nodes are called decision nodes or branch nodes. Okay. And what are child nodes and parent nodes? So for this, if we are splitting this, then these are the child of this node, and this is the parent of these nodes. Okay, so these are the some terminology. What is split variable? So remember, we have splitted this data set using the some variable. Let's say x2, then x2 that attributes or that feature is called split variable, right? And in the case of numerical variable, what threshold you used to split this? Remember in the previous example, we have used x2 is less than or equal to theta 1. So theta 1 was the split variable, split point here. So split point is defined for the numerical feature. In the categorical, how you split, you just take the different categories. Let's say for binary classification, you can split if the feature, let's say feature x1 is categorical. So how you can split, you can say if, and it takes values 0, 1 and 0, categories are 1 and 0. So your node can be as, if it is 1, then all the data set here, and if it is 0, then all the data set here. Okay, so if more than 2 categories are there, then let's say 3, then you can split into 3 parts, but more than 3, then you can group those categories using some or say if they are ordinal, then you can according to order you can group them. Okay, so but generally we are used binary classification problem or let's say up to 3 class classification problem. Okay, so these are the terminologies which are used. Next thing is how to make the predictions. Okay, once we have the tree with us, how you make a prediction. Let's say for this example, where we have make this tree for this particular example, and let's say this example comes. Okay, so how you will make predictions here? So you will go top to down, right? So for here you will check the values of x2. So here x value of x2 is less than theta 1, so it will go to the it will go to the left node. Now you will check the value because this now this example belongs to this node. Okay, so here this node is split according to feature x1. So we'll check the values of x1. So if it is less than theta 2, then it goes to the left node, and if it is greater than theta 2, it goes to the right node. So here it is greater than theta 2, here it goes to in this part, and this in this node we can make the prediction because in this node the green is the prediction. So for this data set, the prediction is green. Okay, so that's how you make the predictions. But the main question is how you build the tree. Okay, so before how to build the tree, one notice this in the building the decision tree, the procedure was recursive. So recursive means what? You start from the top with the entire data set, and then you keep on splitting, right? So recursive means you split the larger questions, the entire data set into smaller parts, and then you again split the smaller parts, right? So in that way, this is recursive, and this is again a greedy search algorithm. By greedy search, because at a step it just takes the max optimal solution. It doesn't matter, it takes the what is the best split for at this stage, right? It only takes care of that. It doesn't makes over, it doesn't look at for overall results. It just takes the optimal solution at this stage. If your data set is here, it takes care of only the optimal solutions here. How to split, that gives you the optimal solutions, right? So it may be the case that some other sequence of split may be the better than this. Okay, so it doesn't take care of about all this thing. In that manner, it this algorithm is greedy search. Okay. Next thing is, okay, so how you build the decision tree. So for splitting the building the decision tree, you need to know what is the split variable and what is the split point. Once you have this thing, you can easily build your decision tree, right? Because if you know what split variable to use and what split point to use, then you can split it. So we need to answer these two questions. We need to find the split variable and we need to find the split point for the numerical. And for categorical, we just need to find the split variable, right? And so for finding this thing, we need a measure. And measure such that it can quantify the goodness of split, because we are splitting in a manner that we want to predict the output, right? So we want to a measure such that it just quantifies the goodness of a split. So if we making this split, let's say for different, let's say using x1 we are making this split, using x2 we are making this split, and there should be some measure that can come that such that we can compare the results of these splits. Okay, so for that measures we will define those measures now, so that we can find the split variable and a split point using those measures. Okay, so for classification we will talk first, and then we'll go for the regression problems. For classification, assume there are k classes. Okay, so one notion here we have defined PIK. So PIK defines the proportion of kth class examples in the ith node. So let's say this is your ith node, and assume only just take one split here. Let's say there are 100 examples, 50 belongs to class 1 and 50 belongs to class 2. And if we make the split such that here only comes 60 example, here comes 40 examples. Such that for 40 here, 40 belongs to 1, then 20 belongs to class 0 or say class 2. Right? So 40 are here, then 10 will be here. So 10 belongs to class 1, and how many? 30 belongs to class 2. So if you find the proportions of 40, if you find the proportions of the class 1 examples here, then it will be denoted by P. I denote the region. So let's say this is first node. So P first and class 1. So it will be what? The proportions of the class 1 examples here, they are 40. So 40 by 60 will be the proportions of class 1 examples here. Similarly, class 2 examples will be 20 by 60. Similarly for this. So this is the notion we define it for defining different measures. Okay. Now the first measure we define as the misclassification error. So as the name suggests, misclassification error is the proportions of the data set which are misclassified in the sample. Okay. So before that, we have to how you will define misclassification error. Let's say you have split this node and you are making prediction here. Making prediction here is class 1. Okay, and you have to class 1 and class 0. And here it was 40 from class 1 and 20 from class 2. So what will be the prediction here? So for predictions, how we will make predictions for the classification, majority majority wins. Okay, so majority class is the prediction class. So here majority are class 1. So the predictions here will be class 1. Okay, so all those examples here are predicted to be in class 1. So what is the misclassification error for this? It's gonna be 20 by 40, right? The proportions of misclassified error in that leaves, right? So overall, this is the misclassification error of this node. Similarly, for this node, you can find an overall misclassification
Will
error.
it be 20 by 40 or 20 by 60?
Sorry, it's gonna be 20 by 60. Yeah. 20 by 60. Right. So overall misclassification error will be what? The weighted sum. So similarly, here it was 10 and 30, right? So 10 for class 1, 30 from class 0. So here what will be the prediction? Prediction will be class 2 because the majority are class 2. So the prediction gonna misclassification error gonna be 10 by 40. Okay, so what will be the total misclassification error? It's just the weighted sum. And what will be the weights here? Weights will be the proportion of examples belonging to those nodes. So if we are taking this nodes here, total 60 examples are here. So what is the weight will be here? The proportion of examples. So weight will be 60 by 100. And what is the misclassification error here? It was 2 by 6, 1 by 3, right? Similarly, what will be the weight here? Here, 40 examples belongs to this node. So 40 by 100. So this is the weight for this node, this leaf, and the misclassification error is 1 by 2. So this is the total error. This way you can do, or simply you can check out of 100 how many we misclassified. Out of 100, only 20 here and 10 here. So 30 was misclassified. So this is your total misclassification error. Okay, so this is one impurity measure, but it is generally not used for the splitting. It is just used for the evaluate your decision tree. Okay, not for the splitting your decision tree. Okay. Can you tell me what can be the maximum value of misclassification error? What will be the maximum value for this misclassification error?
50%.
Yeah, exactly. So as this is the proportion will always be 0 to 1. But as you know, we are making prediction as the majority class. Okay. So the misclassification error is gonna be less than 0.5 for every node, right? And we are taking the weighted sum. So overall misclassification error is again gonna be less than 0.5. So the misclassification error always belongs to 0 to 0.5.
ఇది అయిపోయింది. ఉన్నాయి తీసుకురావే.
Okay, so this is just remember this point here. Now next thing, next measure is Gini index. Okay, so remember we are defining all these for the classification problem only, not for the regressions. That's why we are taking notion PIK here. Okay, so this is defined as PIK into 1 minus PIK and sum over all such classes. So this is for the IF node. Okay, so again that example. Here, if we the same example, if we take 40 from class 1, 20 from class 2. So what will be the PI? Simply say PIK. Okay, so I'm saying only P1, P2. P1 for the class 1 and P2 for the class 2. Okay, so PI will be one gonna be 4 by 6, right? So 4 by 6 and P2 is gonna be 2 by 6. So what is Gini index here? So it is P sum over this quantity. So it is 4 by 6 into 1 minus 4 by 6, which is going to be 2 by 6. And similarly, sum over all such classes P1 and P2. So it is going to be twice of that. Right. So this is the Gini index for this node. Okay. And similarly, you can find the Gini index for this node. And what will be the overall Gini index of this split? It is just the weighted sum. So here it was 60 examples. So weight is gonna be 60 by 100. Similarly, 40 by 100 for this node. This is the weight, and what is gonna be the Gini index here? It will be 1 by 3 and 2 by 3 was the proportion, right? So no, 1 by 3, 1 by 4 and 3 by 4, right?
Yeah.
Yeah. So the gain index of this node gonna be 1/4 into 3/4 and the price of that, right? So if you have asked the gain index of this node, then it is simply this thing. Okay, and if you have to ask, if you have asked the gain index of entire split, the split, okay, so then you have to take the weighted sum of the gain index of this and of this. Okay, so here weights are the proportions. So here it's gonna be 2 cross 1/4 cross 1/4 cross 3/4. Okay, so this is the gain index of the split. Okay, so gain index actually captures the variance over the node. So remember this notion PIK1 minus PIK is kind of variance, right? For the binary classes, binary distributions. Okay, so actually this gain index captures the variance over the node. So for the split, you want gain index to be minimum or maximum. If you want, let's say for two variable x1 and x2, you find if you split your data set for according to x1, then the gain index is coming out to be 0.3. This is the gain index after the split. Okay, and if you split the data set according to x2, your gain index was 0.2. So which one you will prefer to split your data set?
X2.
X2, because x2 is minimum. It means that the variance after the split is the because it captures the variance. It means if you split according to x2, your variance has been reduced, right? So you will check for every possible attributes in the data set. You will find the gain index of the split and will check which is the minimum. If this is minimum, then you will split the data set as per x2. Okay, so this is one measure here. Another is the same kind, but slight difference. Here it captures the randomness in the data set, right? So this is how you define your entropy. This is gonna be minus of this. So this is minus of this thing. Okay, and okay, so this is not natural logarithm. It is log 2. Okay, so this is how you define the same kind of thing, but here you are taking log 2. Okay, so similarly, same manner you can find as you have founded the gain index. The same thing is used, but the expression has changed. Okay, so if you have asked the entropy of this node, then you will just only give this expression, right? And if you ask the index of the split, then you will take the weighted sum of these childrens. Okay, so this is again should be minimum because it captures the randomness. Okay, one more thing here, entropy again takes the values between 0 to 1, 0 to 1, and when it will be 1, when all the classes are equally distributed. 1 means all classes are equally distributed. 1 means the highest randomness. It means all classes are equally distributed. And 0 means the pure node. Pure node means the node contains only one class examples. Similarly, for the Gini index, the values lie between 0 to 0.5, and 0.5 means higher variance. It means all classes are equally distributed, and 0 means pure node. Okay, so remember these things. So remember, misclassification error was highest value was 0.5 for the Gini index, which is 0.5. And for entropy it is 1. So all these values occur when these classes are equally distributed, and 0 occurs when the node is pure node. Okay, now you have the measure. So again, the next measure you can also define information gain is just the change in the measure, impurity measure. So generally it is taken for the entropy, and so change entropy of the parent. Okay, so here it is mentioned entropy of the parent minus weighted sum the this is the entropy, right? Remember this weighted sum of the entropy of children was the entropy of the split. So before split, what was the entropy, and after the split, this was the entropy. So this is the change in entropy. Or if it is mentioned that use the Gini index, then you can also use Gini index rather than entropy. But if it's not mentioned anything, then you just use the entropy. Okay, so this information again we want to higher, right? Because we want this reductions to be higher, right? This change in impurity measure, you want it to be higher. Okay, so once you have these measures, you can find the split variable, right? because you will just check for all every possible variable there. I mean variable means features. So you will check for every features, you will find the gain index and you will check which is the minimum, right? Or for which information gain is the highest. You will choose that variable as the split variable. Okay. So once you have a split variable for classification problem, you are done. I mean for the categorical features, you are done. Okay. So now let's take one example. So before this, I want to just highlight the difference between ID3 and CART. So these are the main two algorithm of decision tree. CART is just the improvised version of ID3. Okay. So you can just say if you know CART, you know ID3. But there was some restriction in the ID3, and we just drop those restriction and come up the better solution for the different kind of problems. Okay. So this is just the improvised version of ID3. So there was some restriction in ID3. What was that? ID3 makes use of only entropy, right? But rather again, it was this restriction was dropped, and we have some different measures as well, gain index or entropy. We can use any in the CART algorithm. Another assumption what made in ID3 was every features was categorical. But again, this features was this restriction was dropped, and we can use restriction tree for any categorical feature and numerical feature. Okay. So these were the main difference between these two. You can just say this is the improvised version of ID3. So if you know CART algorithm, you know ID3 as well. Okay, there's nothing different in the algorithm.
Sir, I have a question. In ID3, can you do a regression tree also?
Generally, in ID3, it's used only for binary classification.
Oh, because there was a question in activity, I don't remember which, but it said that ID3 can use both.
It can be used for both, but generally it is used for only binary classification.
Okay.
Okay, so we are gonna see the CART algorithm here. ID3 goes in the same manner. Okay, so now take one example so the things will be clear. For the classification tree, we are using labels as the categories. So this is the classification problem. Now you have two features. One is X1 and X2. Remember, X1 is the categorical feature and X2 is the numerical feature. So every kind of classification problem will be done using this example. So now this is your data set. How many points are here? Then 10, I guess. So 1 to 10 points are here. Yeah, 10 points are here. So first exam in the root node, you have all those 10 points. Now you have to split this, right? So first split this, you have to find the measure. I'm gonna use gain index. You can use entropy as well. Okay. So first you will find the gain index of the, or you need not to find the gain index of the data set. You can just find the gain index of the split. Okay. Let's say if I use X1. So what if I use X1?
So this last row, it should be a label, right?
Okay, yeah. This is incorrect. So this you can say yes. Okay, so in this, if I split according to X1, right? If I split according to X1, what's gonna be my child nodes? It will be if A, if it is A, if it is B, if it is C, right? So if it is A, what example belongs to this node? This one, this one, this one, and this one, right? So 4 example belongs to this node. And how many belongs to yes? 1 and 2. Okay, so 2 yes and 2 no belongs to here. Similarly, if it is X1 is B, then this example, and this example. So 2 yes, 3 yes, right? 3 yes. And if it is C, then these 3 examples, right? 4, 3, 3, yeah, 10. So it is 1 no, 2 no and 1 yes, 1 yes and 2 no, right? So what gonna be the gain index of this node? You can just directly looking at, you can say it is 0.5 because these are equally distributed, right? What is gonna be gain index here?
0.
0, because this is a pure node, right? And what is the gain index here? It is 1 by 3, 2 by 3 into 2, right? So what is gonna be gain index of a split? If you split according to X1, then what is it, weighted sum, right? So 4 examples belongs here. So weight will be 4 by 10, right? And gain index will be 0.5 and it was 0. So you can avoid this. And for this, the weight is 3 by 10, right? 3 example belongs here. So gain index was this. What is 4 by 9, right? So this is gain index when you split according to x1, right? Similarly, you can find if you split according to the same examples. So here it was yes. So this is when we split according to x1. What if I split according to x2? Now it is the numerical feature, right? So how you will split according to numerical features? You have to find two things. One is a split. Okay, split variable we are already talking about. Now we have to find the split point as well, right? So what are the different possibilities of split point? So a split point are the different values that are taken by the examples, training data sets. Okay, so all those different unique values which are taken by x2 will be the candidates for split points. Okay, so all such possible points you will check the Gini index. Okay, so I'm taking only one. You can check for every possible values here. Okay, let's say the split point is 88. Okay, so if the split point is 88, then what will be my child node? So the left node will be according to if it is less than or equal to 88, and the right node gonna be greater than 88. So all those examples where x2 is less than or equal to 88 belongs to this node, and all those examples for which the x2 is greater than 88 belongs to this node. Okay, so once we have the data set, we can find the Gini index. Okay, so for this I'm doing for all such possible values you can find the Gini index, and for which split point it is minimum, you can choose that as a split point. Okay, so for 88, let's say this one.
What is the criteria you are getting here to decide the point is 88?
No, so for you find the split point, you will check for every possible value here. Okay, you will check for all such possible values, and for which it is minimum, you will choose that as a split point.
Okay, so all the values what are mentioned here, like 90.5, 95, 70.5, everything
So
I need to check.
Yes, yeah. For every possible values, you have to check the Gini index. Okay, and for which it is minimum, you will choose that as a split point.
Okay.
Assume that 88. I'm assuming only 88. Okay, you can do for every possible values and check for which it is minimum.
Okay, and here why we are splitting at two branches? Why not three? Like x2.
No. For numerical, always binary classification is there. Binary, I mean the binary split is there.
Okay, so equal to always be with less than.
Generally, it is taken here, but it's your choice. But generally, it is taken on the left node.
Okay.
I mean the less than or equal to 88.
Thank you.
Okay, so these three or four example belongs here. This one as well. Okay, so again, so 1, 2, 3 no, and 3 yes. Okay, and similarly 1, 2, 3 yes, and 1 no belongs here, right? So you can find the Gini index when you have a split point 88. Let's say this is the minimum for the this is the minimum for 88. Gini index is minimum for 88. So your split point is 88. Now once you have the Gini index, you will check for x1. So x1 was let's say it was some value. So this was some value. Let's say x1, and this is some value x2. Okay, so you will check which is minimum. If it is minimum for this one, then your split variable is x2, and if it is x1 is minimum, then your split variable is x1, right? So once you have a split variable, you can split your root node, and then again you can start with these nodes. You can start splitting these nodes. Okay, and in that manner you can build your full size tree. Okay, any question here? How to build a classification tree? It should be okay. We have covered classification tree for both categorical variable and numerical variable.
Sir, I have one question. So for x2, what will be the total Gini for x2? We have to find it for all the numbers.
Yes. Once you have a split point, you choose the minimum, right? For every person you have find for 90.5, 95, 70.5, all such values, you will choose which is the minimum, right?
Right.
Let's say it is minimum for 81, 88. Okay, and this is coming out to be x2. So your so if you split your data set as x2, your split point gonna be 88.
Yeah, so that is with respect to x2. Now I am going with respect to x1 and x2. Which one shall I choose for the root node? In that case, how will I understand for
So
x2?
since if you split as x2, your gain index gonna be what? X2, right? Gain
Yes.
index of a split. And for if you have a split according to x1, your gain index was coming out to be x1, right? So so you will compare these values. This is minimum. If it is this, if this is minimum, you will split according to x feature x1. If this is minimum, then you will split your data set according to x2. And for x2,
Okay.
the split point gonna be 88. Okay. So this is just numerical feature is little more involved because for every possible values you have to find the Gini index. Here it is just categories, different categories. So you need not to worry about because for every possible category you have different nodes, right?
So here, since it was about the root node, we found the total entropy. Suppose if I want to do it further on, I mean, somewhere in between. So do I still find the total entropy and then decide which one?
No. So once you have split your root node, right?
Yeah.
Let's say you have split and this one your child node. Okay. So some data belongs to here, right?
Yes, sir.
Okay. Let's say this 5 data set. These 5 data set belongs to this node, and you have to split this node. The same procedure you follow.
But
same
now
problem,
how,
right?
sir, but sir, I find the entropy, I do the weighted sum of entropy for the entire data right now, now for this, or only for the from this child parent node I do it.
Now it's the same problem, right? Once we have the entire data set and we want the split variable, right?
No, like you said, sir, in this particular thing, we have the first 5 examples there. So now would I consider only the first 5? So for the proportion for the weighted thing,
Yeah,
I would
only 5.
only the first
Only
5.
5, right?
Okay.
So this is your, in that case, this is your node and this is the child node of this parent. Okay.
Okay. Okay, sir. Yeah.
Okay, so this is all about the classification tree. So you should be able to build a classification tree given the features.
So sir, for finding out the overall gain index for this x2 feature, so we will have to find the weighted gain index of each and every value, right? For 90.5, 95 for
Yeah,
finding
for
the
every possible values, because you have to find the split point as well, right?
yes.
So the possible candidates for split points are these all unique values.
Okay.
So for all possible candidates, you will find the gain index.
Okay. And then finding the weighted sum of this gain index value for this, finding the whole overall gain index for this x2.
Yeah. So once you have, let's say you have split according to 88, you have these 2 child nodes. So you will find the gain index of this one. You find gain index of this one, and what will be the gain index of a split? It is gonna be the weighted sum of this.
Okay.
Okay. Okay. So this is classification tree. Let's talk about the regression tree as well. So for classification tree, we have 3 measures, right? One is gain index, one is another is in entropy, and another is information gain. So you can use any of these 3. Information gain is just the change in the entropy, so it doesn't make any difference if you use gain index or information gain or the entropy or information gain. So you better to use only gain index or entropy. It's your compatibility, how you are comfortable with. Okay, so if you are comfortable with information gain, you can choose that. Otherwise, the gain index itself is sufficient or entropy is sufficient, right? But now, what about the regression? What do you think gonna be the impurity measure here?
Variance, weighted variance.
Yeah, variance, or you can say the sum of squared error.
Sum of square error.
Right? Any of these 2 you can choose. Okay. So remember here we don't have the classes. We have only the real values. So you have to find the variance within those values. Okay. So once we have the measure, now the same thing. Okay. But the measure has changed. That's the only change here. So same problem, but the now prediction has the labels has changed. Now labels is the final score, final exam score. So now this is your regression problem because we have the real values as the as the outputs, right? So again, the same feature, same categorical features x1 and numerical feature x2. So let's say you have to decide what is the split variable at the root node. So what you will do, you will again choose, you will go over all possible attributes. So x1 or x2. So let's say I'm choosing x1, and again I will find the not gain index, the variance for x1 and x2. So if I split according to x1, it is gonna be A, B, and C. Similarly, you have three the same kind of thing. You have how many examples? So, right. So 2, 2, 3, and 1, 2, right? Okay, here it is not by yes and no. So here you have to take the, so what is gonna be the predictions here in this node? For the classification, you make the prediction as the majority class, right? So since if
Mean,
you're
it will be the mean, sir.
yeah, so in the case of regression, the prediction is mean. Prediction is mean. Okay. So so how many examples belongs to here? 4 examples, right? This one, this one, this one, and this one. So you will take the mean of this one, this one, this one, and this one. So let's say the mean is coming out to be 55, 81, 88, 42. Let's say it's coming out to be 65. Okay. So what is gonna be the sum of squared error here?
You have to subtract the mean from each of these points
actual
and
minus
square it.
predicted. So predicted
Yeah,
was 65 and actual was 55. So 55 minus 65 square plus similarly is 481, and this one whole square. Sum of squared error for all such values. Similarly, you will find the sum of squared error here, sum of squared error here. So in one go, you can find the sum of squared error variance. You need not to worry about the weighted sums, right? So here again, let's say B for B, right? So these two and this belongs here. So 72, 66, and 86. So let's say what gonna be 75 is the predicted value here, the mean of these three. Okay, and so this is gonna be 72 minus 75 square. Similarly, for this thing, you have these two values, these three values. Let's say the variance is whatever that is 60. Let's assume. So you take the sum of squared error, right? And this is gonna be SSC for this split. Again, you will find this is for x1. What if I split according to x2? So similarly to
Sir, here, sorry to interrupt, sir. So now you found the SSC here. This again for the entire data set will be a weighted sum, right?
No. I have taken the sum of squared error here. All such I'm taken in one go. So for this examples, it belongs to here, right?
Yeah.
So actual was there. The prediction was 65. So what is the error? 55 minus 65. Similarly, for this example, this belongs to here. This belongs here, right? So actual was 45 and the predicted was 60. Right? So this is the error.
But sir, that is for each node that I am getting, right?
Yeah. So this is in total, right? For every examples, you have find the error and taken the sum of squared of those errors.
Okay. And then I basically sum it all up. At each node, I take it and then sum it up.
Sum it up.
So here we don't add any weights or anything, right, sir?
No, nothing.
Okay.
Okay. So this is for categorical feature. What about the numerical feature? So you have to find the split point as well, right? So similarly, you have all these unique values are the possible candidates for split point. So for every possible points, you will find, let's say, okay. So I'm just removing all these things.
So this for this it will be the same. X2 will be the same what we did before, right?
Yes, same thing. Just the measure has changed.
Measure has changed. Now, how will we select between X1 and X2? Which one to split on? Because
so
there we had
you want
any
variance to be minimum or highest.
So how will you add across A, B, and C? You're going to add the sum of squared error for A, B, and C.
So sum of squared error I have found for every possible examples, right?
Yes, but for A you have found separately, for B you have found separately, for C you have found separately.
No, I have added all those. This is error was the adding for every possible examples.
In A. For A. For
Yes,
A,
so-
you have added.
Yeah, for B also I added. For every possible example, for all 10 examples, I found the error.
Right. Now we've
And
got 3 errors. One for A, one for B, and one for C.
Just add those up.
We have to add those up. Okay.
Yes, that's it.
And we don't have to take
Addition of-
the average of that? Or no.
No, you need not to worry about those.
Okay.
Okay. So once you have the variance of this split and split for x2, what you will choose? Minimum or the highest?
We'll need the minimum.
Minimum.
Okay.
You want variance within the variance that error to be minimum, right? Sum of expected error. Or the
Right.
variance to be minimum. So if it is minimum for x2, then you will choose x2 as a split variable. And if it is minimum for x1, you will choose x1 as a split variable. Okay. So only point is for classification and regression both, for numerical features, you have to take care of all such possible split points, right?
Right.
So any doubt here? So up to now, you should able to build a classification tree and regression tree both. Whether you have been given categorical feature, whether you have been given numerical feature, anything, any data set you have been given, you should able to build a tree, whether it is classification tree or regression tree.
Sir, unlike Gini and entropy, we don't need to do proportionate SSEs for each of those A, B, C.
No, nothing.
Okay, whereas if you did variance reduction, I think in one of the solve with instructors for variance reduction, we had taken proportionate value for each of the possibilities.
No,
I
it
don't
won't
know.
affect it won't affect your split as because remember here we are making predictions as we are taking the error. So here we have different predictions for different nodes, right?
Right.
So here it was 65, here it was 70, here it was some 80. And for you are taking one example here, first example. So you are taking which node it belongs to. If it belongs to here, so here prediction was 65, but the actual was 55. So 55 minus 65 is the error. So you will find error for all 10 examples, right? So you have the error for 10 examples, but this is not case for the classification problem.
No, so if you were to do information gain with SSE, would you still follow the same approach? So you will calculate the SSE at the overall level minus.
No, information gain is not defined in case of regression problem.
Okay,
or
so
you can just refine the change in variance, but that is not called information gain.
Okay, so it's called variance
You can
reduction.
still
And that's
define the change, but that is not called information gain.
Okay.
Sir, in this X2, if we do,
Yes.
in this case, we will get 20 SSEs, right?
Or 20 SSEs. How? 10 only.
Because for every point, I'll have binary 2, greater than and less than.
But the overall SSE gonna be 1, right?
Yeah,
so
I'll add them up and it'll be 1.
Yes.
So I'll add
this
20.
This need not to be 10. It's just the unique values present here. Okay, since 91 is repeating, 95 is repeating.
Yes.
So all those unique values are.
Yeah, only unique. Yeah, if I subtract the unique value, I mean, if I only take
obviously
the
this
unique
is gonna
value,
be unique.
into
Doing
2,
same thing
and I'll add them up.
Yeah.
Okay.
Right. So if you have asked the variance here, so what's gonna be variance here? So final predict. So first prediction is always average, right? So you take the average and then you can find the variance for the root node. So it's not, we never check for the change reduction in variance or reduction in SSE, but generally just check the sum of square error, and for which it is minimum, you can choose that split point and you can choose that split variable.
So the only difference between variance and sum squared error is that we take the mean in variance. That's all, right?
Yes.
Yeah.
Should we not consider IG for determining root node? So IG is just a change in entropy, right? Or change in Gini index. So it's gonna be the same thing. If either take the highest information gain or either take the minimum Gini index or entropy, right? So this is gonna be the same thing. So whether you can choose information gain or you can choose Gini index, and recording will be shared. I mean it's present on the YouTube. Sorry.
Recording is not being correct.
I'm not getting. I'm not able to listen. Can you write it down on the chat? Recording is not live stream. No, sir. This is not recorded. Okay. Let me inform the student. I mean the team for that. Give me 1 minute. Okay, so I have informed the team. They will take care of this. If it is not streamed, then they will take care. They will upload the recording later. Okay, so okay, so till now you should able to build your tree. Now the main things. Now we know how to find the split variable, how to find a split point, but when to stop your tree. Okay, so one point is if all the leaves are pure node, you definitely will stop your tree, right? Because you need not to split again. Once you have the pure nodes, you need not to worry about the splitting. Or no further splitting is possible, then again you can stop your tree. So let's say for one example, you have x1 feature, x2 feature, you have classes 1, 0, 0, 1, and for x2 you have classes, let's say 2, 3, 3, 2, and you have label as yes, no, yes, no. Okay, so let's say I split my data points as x1. So if x1 is 1, it's 0. So in this data points, how many data point will be here? This one and this one. So first 10 second belongs to here, right? And so you have yes and no here. And again for this node, you have yes and no, right? So if you want to split this data point, so which feature you will use? If you use x1, then you cannot split according to x1 because all the values okay, so for this node, you have values as 1 and 1 for x1. So according to x1, you cannot split. Similarly, for if you split according to x2, the values are 2 and 2. So for again, you cannot split this node for x2. So you don't have any possible features to split this node. Even though this node is not pure, you cannot split this node further, right? So no further splitting possible. In that case, again, you have to stop your decision tree. I mean the splitting of decision tree. Or some threshold we can define. So this comes under pre-pruning. You don't grow your full size tree. You just set some threshold. Threshold can be the number of examples in leaves, right? So these are leaves. Let's say these are your leaves, 3 leaves. You can set some number of examples. At least this number of examples should be there in the leaves. One kind of threshold. Or you can say the reduction on the error or reduction in the gain index or reduction in the SSE should be at least this much. This kind of threshold you set for splitting, right? So some user defined threshold you can set to stop your tree. Okay, so this is the stopping criteria for a decision tree. Okay, so what is the size of a tree? Size of a tree is defined as the length of the longest path from the root node to a leaf, right? So let's say this is your tree. Right. So what are the leaves? This is leaf, this is leaf, this is leaf, this is leaf. So the longest part. So this is length 1, this is length 2, this is length 3. So what is the longest part? This. So the size of a tree is 3. Okay. So the longest part from the leaf, from the root to the leaves. Okay. And if the size is less, right? If size is less, so then it will be underfitting. And if the size of it is more, then overfitting. So these 2 points make sense. Right? Similar size is less than means you're not growing tree for further, right? So you have less number of leaves in the data set, so you have less number of split. So there you don't have the better split or better you have higher error, you can say. So in that case you have higher training error. So less if the size is less, then it causes underfitting. If size is more, then it causes overfitting. Because in that case, if you split further and further, remember, tree stops when when all the leaves becomes pure. Pure means zero training error, right? So zero, all the leaves are pure, then it is gonna be give you the low training error. So it causes the overfitting. So generally, decision trees are prone to overfitting because every decision tree keeps on splitting until it stops itself, right? Or all the nodes becomes pure. So that's why decision trees are always prone to overfitting. Okay, so this is one disadvantage of the decision tree. That's why decision trees are not generally used in practice. But we can overcome this problem of overfitting. So let's see that. So overfitting is the main problem with the decision tree. Okay, so why it happens is just because the specificity. So by what I mean by this, remember for each and every node, we try to split that node for every possible values, right? And for every possible features. So we can keep on splitting till it goes to the longest path, the highest size of the tree. So in that case, we keep on doing splitting and the training error becomes very low. And that's why this is decision trees are prone to overfitting. But whenever the training error is low, the chances of the testing error will be higher, right? So it or you can say the decision tree learns the data set very well, the training data set very well. And that we have seen in the first slide, right? And I've said that it is a problem as well because it's non-parametric because we don't take care of the distribution of the data set. It learns any kind of distributions very well, but it's an advantage. But disadvantage is that it learns in a manner that training error goes very, very low and it causes overfitting, right? Data set very well. So this is the problem with decision trees. Now, how to overcome this? Okay, so just give me 1 minute. Okay, so okay, so how to overcome the overfitting here? There is two methods. One is called pruning and one is called ensemble. So ensemble we are gonna cover in the big 10. And pruning is two types of pruning is there. Pruning is just cut down the tree. Okay, so there's two methods: pre-pruning and post-pruning. Pre-pruning is you don't grow the full size tree, right? Don't grow the full size tree, but just user defines some threshold and just stop splitting the full size tree. That is called pre-pruning. Okay, so generally it is not followed just because there is how to decide the threshold. This becomes a hyperparameter, and again we are not sure whether we are able to overcome the overfitting or not. Okay, so pre-pruning generally not follows. Another is called post-pruning. So post-pruning, in the post-pruning, what we do, we grow the full size tree and then prune back. Okay, so there's one method of post pruning which is covered in this week. So this is called cost complexity pruning. So what happens here, we grow the full size tree, let's call it T0. Okay, full size tree, and then prune back. Okay, so let's assume you have a full size tree which is T0 and then prune back. And for how to define, for that we define one measure which is called cost complexity measure, CT, and it is defined as sum over QIT. I'm coming to that. What is this? Plus alpha times number of leaves in that tree. So T, let's say T is your subtree of T0 after the pruning back. So let's assume this is your tree, the simplest tree. Okay, so this is your tree. Now you prune back. Prune means this is full size tree. Now if you prune, so pruning is that you just remove these two nodes. So you have come up with this tree, right? So this is your T1 now. Let's say call it T1. Okay, so T1 is T0. So you define the measure here, T1 here, and it is defined as this is called misclassification error, right? For classification on for SSC for the regression problem, and this is the number of leaves, okay, in that tree. So in this tree, how many leaves are there? 1, 2, and 3 leaves in here, and this is called complexity. Remember, if the number of leaves are higher, then the tree is more complex, right? Because it keep on splitting further and further. And if the number of leaves are less, then your subtree is less complex. So this mod of T is called complexity of the tree, and this alpha is called complexity parameter. Okay, so this is a hyperparameter.
Why are we taking mod? It'll always be a positive.
No, mod is just a notation for number of trees. It is just a notation from number of leaves. Okay, it's not the T is just a tree, and the mod of T denotes the number of leaves. It's not taking.
Sir, and the Q1 of T is the impurity measure, is it?
Yeah, impurity measures for this subtree. So in subtree you have misclassification here, and here, or for SSC you have just take the sum of our SSC here, right? Okay, so you want this error to be minimum. Okay, so alpha complexity parameter, it should be a hyperparameter. Actually, it is a hyperparameter, and alpha can take any value between 0 to infinity. But if you take alpha 0 means what? You want to minimize this error. You want to minimize this means you are minimizing this. And when it can be minimum, when you have full size tree, right? So alpha is equal to 0 means you don't pruning back, right? And you have full size tree. And what if alpha tends to infinity? I mean, it goes very, very large. And when it will be minimum? Alpha tends to infinity. So you have to make sure that this goes to 0, right? Because it's becoming large. So you want to minimize this. So you have to make sure that it tends to 0. It means number of leaves are going to 0 means that you have a root node. Right? So you don't want alpha to be very high. You don't want to alpha be very 0. For a given alpha, you choose for all possible trees. You have always finite number of trees, subtrees, T1, T2, T3, Tn. Let's say these are your finite number of trees, and you will check the value of CT. Okay, for a given alpha, you check the values of CT, and for which it is minimum, you will choose that subtree. Okay, rather than full size tree, that subtree. Let's say for T3 is minimum. For some different values of alpha, you do the same procedure and will check which gives you the less CT value. That subtree is taken as your final tree. Okay, so that's what happens in cost complexity pruning. Okay, so if you don't have any doubt, we can go to week 10 because we are already late. We are not. We are 9.
Basically, alpha regulates your overfitting.
Yeah, overfitting.
Okay.
Okay, so this is a hyperparameter which is learned using cross validation techniques. Okay. So I think week 9 is all. Everything is covered in week 9 now. So you can build your tree, regression tree, classification tree. You can overcome the fitting using the pruning. One more technique is there to overcome the overfitting, which is called random forest, that we are gonna cover in week 10. So any doubt in week 9 you can ask. Otherwise we can move to week 10. And I don't think we can cover it into.
So what kind of questions can we ask from week 9? Is it kind of building the tree from the chart, or we have to calculate the complexity of the pruning? So
No. That kind of complexity, because complexity you need to define subtree. Then how you will define subtree? How you will define alpha? So there is many factors there. Okay, so such kind of question will not be asked. Much complex question will not be asked. If there are some numerical questions, that's gonna be very easy kind of questions. Okay, not you should know the concept, how to find Gini index, how to find the information gain and all. So
okay, so cost
easy
complexity
calculations
will not become, you are saying?
It can come, but some conceptual question will be there. It's not like compute the cost complexity of the tree.
Okay. Thank you.
Okay, so let's move to the week 10. Okay, so week 10 is ensemble methods. So what is ensemble? As the name suggests, ensemble means you just collect the results from different estimators. Okay, you just combine the results from the different estimators. So combining results, right? So you so does it make sense to combine the estimator which has the better performance? I mean the good accuracy or good performance? Doesn't make sense. Okay, so what we do in ensemble method, we take the estimator which are very weak learners, or say very have very low performance. Okay, just like decision tree. As decision tree is prone to overfitting, generally decision trees are used for the ensemble methods. Okay, so we take different decision trees for a particular training data set, and we just combine those results. And what I mean by combining, if the classification there, so for let's say n estimators you have defined 1 to n estimator, so classification you have made n predictions from those n estimators, right, or classifiers. So in classification, how you will make the final prediction? Just a majority wala, right? So take the majority predictions and you will taken as the final prediction. And for the regression, you take the average. Okay, so this is what I mean by combining those results. There are two kind of ensemble methods. One is voting and one is boosting. So voting, what happens there? In votings, we take the high variance estimators. You remember decision trees have high variance, right? Overfitting. Right. So you take different decision trees, combine those. So vote among means vote means combining those, right? Majorities or average. And boosting means you define a weak learners. Weak learners means just whose performance is just better than the random estimator. Okay, what is a random estimator? Whose you just randomly give any predictions to that. Let's say for binary classification, you take one example, you randomly assign prediction there. So what gonna be accuracy there? If you take the random estimator for the binary classification, 0.5, because you are randomly making prediction out of two classes. If it is 3 classes, then accuracy gonna be 1/3, right?
1/3.
So out of 3, you are randomly giving one predicted value, right? So the weak learners are the learners whose accuracy, or say whose performance is just better than the weak random estimators. Okay, so you boost them. Boost means you just try to overcome, or you just try to rectify the error that a weak learner is making, and you sequentially keep on doing this thing. Okay, so you boost the your estimator, right? So remember, in voting, we are taking voting. So every estimator you can run in parallel. Okay, every estimator can be learned parallel. Okay, but in the case of boosting, you just boosting the weak learner, so it goes in sequential manner, one by another. Okay, one by other. Okay, so here they are independent, they are learned independently, and in boosting they are learned in parallel. Independent. They are dependent to each other, because the next model is or next estimator is learned depending upon what error the first estimator has made. Okay, so how we do that? That is gonna be covered in week 10. Okay, so first we cover voting.
This boosting and ensemble is for overfitting problem, right?
Yeah, for those estimators which generally have overfitting problems like decision trees. Okay, so we never ensemble linear regression or logistic regression. Decision tree are generally used for ensemble methods.
But boosting is not kind of underfitting criteria.
No. Boosting is generally used for weak learners, like decision tree with very less size.
Then if it is very less size, then how come it becomes overfitting?
No, weak learners means that have very less performance. So yeah, so those weak learners may underfit, not overfit.
No, that's what I'm trying to understand. Like these two methods are for overfitting, overcoming the overfitting, right?
No. These learn those estimator which overfits, and these learns those estimator which underfits. So very first estimator is underfits because it has weak learner. It is a weak learner. Now you will rectify this. Okay, so there we have one estimator. Now we are making another estimator using this using the error that this made. Okay, here estimator are not independent. They are built using the previous estimator. Okay, so very first estimator you can say that underfits.
Okay, so here you mean to say the estimators are weak.
First estimator, the very first estimator of the boosting is has the underfitting problem. Then second estimator is made using this estimator. Okay, so we'll check which are making errors. Okay, we try to rectify those. We will come to that in AdaBoost algorithm and gradient boost algorithm. Okay, how we are doing this. So that then the idea will be clear. Okay. Okay, now we will cover voting first, and then we'll go for boosting. Okay, so voting, as I told, we define n classifier. This is your training data set. You define n classifier, and for n classifier you take the predictions, and how you will take final predictions. This is the n prediction. You take the vote over these. So for classification you take the majority class, and for the regression problem you take the mean. Right. So this is what I mean by voting. So in voting, one technique is called bagging. Bagging stands for bootstrap aggregation. And what is bootstrap? Let's say you have this training data set. So you will create if you have to build n estimator. You create n different bootstrap samples. Okay, so assume n is 3. So you have to design 3 estimators. So you will create 3 bootstrap samples, and bootstrap sample is nothing but the sampling with the this is the you have 10 points here, right? You with the replacement you take the samples. So let's say this is your first bootstrap sample. So randomly you choose 1 point here. So x8 comes here, then x6 comes, x2, x9. So remember x2 is again repeating. So you take the samples, you do the sampling with the replacement, right? And this left in the sampling. Okay, so these are called out of bag data set. Okay. Similarly, you create second bootstrap sample, again the same kind of thing, and the number of samples. Remember, in the number of samples, it always same. Here, if in the training sample, 10 points were there. So in every bootstrap samples, you take the 10 samples, 10 here, 10 here, and 10 here. But just because they are taking with replacement, these gonna be different, right? This is not gonna be same, but the different. Okay. And why we are doing this, we'll come to this later. Okay. And so the first step is you just create the bootstrap sample, and then over those n bootstrap samples you learn your models, n models. Okay, so one technique in bagging is random forest. So remember steps. One is create the bootstrap samples, Then over all those n training data sets and different training data sets, you learn n different estimators. And as I told you, the estimators are nothing but decision trees. Okay, so what you do for every n training data set, you learn n different decision trees. Okay, so these are the steps. First, you create the bootstrap data sets. Then you create the decision tree using that sample, that data set, right? But here, remember, for creating the decision tree, don't use every features. Use some random subset of that features. Okay. And then again, repeat these things. If you are to find n estimators, repeat this step n times. Means you are learning n estimators, and these steps can be learned in parallel. Okay. So let's take one example. Then okay. So one more thing, random forest generally can be used for classification and regression, but in this course we are only concerned with the classification problem. Okay. So how we make predictions? Similarly, because it's a bagging or voting ensemble methods. So for classification, we take the majority out of n estimators, and regression we take the average. Since it is a bootstrap plus aggregation, it's a bagging algorithm. Okay. Now take one example, then it's gonna be easy. So you have this training examples. Okay, so 14 training examples here. You have a classification problem, 4 features, x1, x2, x3, x4. The x2 is now numerical features, and all 3 are categorical features. Now you have to learn the random forest using this example. So what were the steps? First step was create the bootstrap sample. So I created one bootstrap sample here. So remember, in bootstrap we take the samples but with replacement. So here we have taken the bootstrap sample. Remember, first sample was D1, another second sample was D9, D3, D1. D1 is repeated again, D14, D6, D17. So we have created one bootstrap sample. Now what was my second step? I need to create a decision tree, but with I'm to use some random number of features. Let's say I'm taking 2 only. Okay, so I'm taking only outlook and wind. Now you have reduced to this problem. You have this data set. Now you have to create the decision tree. That we can do because we have already know how to create a tree using a decision tree. Let's say this is coming out to be this one, decision tree. Okay, this is T1. Okay, you can repeat this thing. Now again you will take the bootstrap samples. Again you will take a random sample. In that case, let's say for T2 I'm using a temperature or humidity. Okay, so again I will define T2. I can, in similar manner, I can define n trees, T and Tn. So once we have Tn, now we can define the make the predictions, right? How to make the predictions? We will make the predictions over T1. Let's say one example comes. Let's say this 14th examples comes in. Okay, so you will find the predictions for T1. You will find the prediction for T2. For Tn up to Tn, you will find the predictions. And what will be the final predictions? The majority class, right? Over all such n class, majority wins. Okay, so how you will evaluate? So evaluate. Remember, we have created the decision tree, right? So we have created the bootstrap sample. So in creating
one doubt here, sir.
Yes.
This there'll be 2 majorities here. One will be within the T1 for n samples, n bootstrap samples.
No. For
right?
let's say for this example, I'm to make predictions. Okay. So what is the
So you
prediction?
have n bootstrap you have selected, and you'll do for all those n bootstrap.
Yes. So for this example, let's say prediction was yes. For this one, it was yes. For it was no. And let's say for out of you have learned 10 estimators, and 7 was yes and 3 was no for this particular example, right?
So we'll
7,
use only one sample for T1.
For
Okay.
this example, prediction was yes. For this example, again you will go over n estimators.
Okay.
Okay. So in that manner, you will make the predictions.
Okay.
Okay, so for evaluating, you use the out-of-bag data set. Remember what was the out-of-bag data set? In Bootstrap, generally 1/3 of the data set remain unselected. So that data set generally used for the testing or evaluating your model. Okay. So now can you create the decision tree? I mean the random forest. It's easy. Remember 2 things only. always always take the bootstrap sample, and the second thing, always take never take all the features. Always take some subset of the features to create the decision trees. And every time for every estimator takes different subsets, not the same subset. And why we are doing that? Why we need subset? Why not every features? And why we need bootstrapping? Because if don't take if we don't create bootstrap and don't create subset, then every estimator gonna be same, right? And it doesn't make to average out the estimator which are giving the same performance. So just to make sure that the every estimators have different performance, we take bootstrap samples and we take the subset of the features. Okay, so how to choose that number of features to make the decision tree? This is one hyperparameter in the case of random forest. So generally it is start with root m. Root m is total number of features. In our case, we have 4 features. So 4 features we generally start with 2. Okay, and we for 2 we find the random forest. Now we can go up and lower. For that value for root m, let's say root m plus 1, root m minus 1, something like that. And for such possible values, we take the we evaluate all those random forests and we'll choose one which gives the best performance. Okay, so that idea should be clear why we need number of features and why we need bootstrap samples. Okay, so tell me, if I choose lesser number of features, then their performance will be more dependent or independent. I mean, the performance will be same or more different if I choose less number of features.
Your performance will be less, I think.
Performance will be different, right?
Yeah.
And if you choose large number of features, then your performance gonna be kind of same. That's why we use less number of features to create your decision trees. Okay. So this is all about the random forest. So any doubt in bagging or random forest?
How many features we choose randomly?
So random number of features is generally a hyperparameter.
Okay.
Okay. And generally it start with root m. We go just a few values above, few values down, and just check the performance over those values and choose one which is giving the best performance or the least error, you can
So
say.
this last point is not clear. If you choose less features, then the performance will be different. And if we choose larger features.
Okay, tell me, if you for creating different estimators, if you have used all the features,
yeah,
then
so
their
I'll
performance
get the
kind
same.
of same. Yeah. So if you keep on reducing number of features, their performance may be different.
Okay,
right?
okay.
Because
now
you have
got
used
it.
different number of features, and every time for every estimator, you will use different number of features and different number of different features. Okay.
Right.
So let's say for T1 I've used outlook temperature. For T2 I can use temperature, wind, or T3 I can use any two and kind of thing. Okay. So in that way their performance may be different.
Okay. Right.
Okay. So now let's move to the boosting. So we have done voting, now boosting. So remember, in voting, we can learn every estimator independently. So their learning process can go in parallel, but it doesn't happen in the boosting. So in the boosting, we learn an estimator, we check the error, then we build the next estimator. Depending upon what error estimator.
So I can't hear you.
Yeah, can't hear.
Is it better now?
Yes, sir. Now it's clear.
Okay. Okay, so any doubt in voting? Okay, so we were talking about the boosting here, right? So in the boosting, what we do, we learn, we start with a model. Okay, we build a model, then we'll check the error of that model, and then for rectifying that error, we make the second model. And how to do that, we will come to that. And so generally, we start with a weak learner. Okay, so what is weak learner? We have already told you. Whose performance is slightly better than a random model. Okay, so we start with the weak learners. One of the example of weak learner is stump. So stump is decision tree with one split, right? So if you have only one split, this is called stump. Okay, so in this stump, remember this is a weak learner because it will give the just slightly better performance than the random model. So for boosting, we generally use the stump or the trees with the lesser size. Okay, so there are two algorithms in boosting. One is called adaptive boosting and other is called gradient boosting. Okay, so in AdaBoost, we use weak learner as the stump. Okay, so what is your what happens here? We make a stump. I mean, we make a decision tree with one split, and for making a stump, we give the equal importance to that point. Then we'll check the error of that stump. Okay, so or save the performance of error. So what is the error for that stump? It is the sum of sample weights of incorrectly classified samples. So it's nothing but just the proportion of misclassified points. Okay. So again, AdaBoost generally used for classification, and we will cover only classification problem here. Okay, so what is this sample weights? For making first system, we give equal importance to each and every examples. I mean, if there are n examples, we take the sample weight as 1 by n. It means that we are giving the equal importance to each and every examples. Okay, and what will be the error? Will be the proportion of misclassified points, and the performance is defined by it is called alpha. Alpha is defined by 1 by 2 log of 1 minus error upon error. Okay, so this is how you define the performance of a system. Okay, so if you draw the curve between total error versus performance alpha, so it is coming. So let's say it is 0 here. So it comes like something like that. Something like that. It comes something like that. Okay, so if the higher error, if the total error is higher, then the performance goes in negative. Okay, so negative means performance negative means your stump you have, and if you have error very low, it means you have a higher performance. Okay, so it makes sense. Higher error, I mean the higher error, very bad performance. If the once you have done this, stump is just a decision tree with one split. Okay, so these are called stumps. Okay, so as I told you, in boosting, we just try to classify, we try to rectify the error. So once we have defined the error or we define the performance, we will take the misclassified samples and then we will give the more weightage to those misclassified points, because now we want to rectify error. It means we want to classify misclassified point correctly. So we will give the more weightage to the misclassified point in the training the next stump, and we will give the less importance to the points which are already classified correctly. Okay, so that's how you will make the second stump. Okay, so how to define those, how to increase those sample weights, how to decrease those sample weights, that is the part of this learning algorithm. Okay, so this I will come to later. Just okay. Okay, I forgot to add example here. So classification example, can I make use of this thing? Okay, so let's make use of this thing to understand the AdaBoost. I should have added this. I don't know why. I forget that. Okay. Let's use that example then. Okay, so first we will create the first system. Okay, so first system, let's say this is your first system. Okay, so first system is your decision tree, this one, and in the first system it is Outlook, and this is your tree. And for first example, we take the equal importance. So there are 14 examples. So I will take 1 by 14, 1 by 14. Here we need not to take the bootstrap samples. Okay, so assume there are different examples. 1 by 14. So all these have equal weightage. Okay. So now error will be, let's say you have Outlook, and so Outlook is Outlook, then sunny, overcast, and rain. You have 3 child nodes, right? Sunny, overcast, and rain. Okay, so how many examples belongs here? How many examples belongs here? You depending upon you make the predictions, and let's say yes, no, yes are the predictions, and you find the error. Total error will be your misclassification error. Okay, and then you will define the alpha. So alpha is gonna be 1 by 2 ln 1 minus total error upon total error. So this is the performance of the system. So higher the performance means it's working very well. It means it has low error. And then for creating the next system, you make use of this. You now give the different weightage, different sample weightage. Okay, so for creating the second system, I will assign different sample weights now. Okay, so for misclassified point, I will increase the sample weight. So by what factor I will increase? It's gonna be 1 by n e raised to power alpha. By this factor, I will increase my sample weight. And for the classified point, I will decrease my sample weight by 1 by n e raised to power minus alpha. Okay, now let's say the alpha is coming out to be, performance is coming out to be 0.9, very good performance. In that case, if this example is, let's say, correctly classified, okay, so in the next sample weight gonna be 1 by 14 e raised to power minus 0.9. Okay, for let's say this example got misclassified, so in this speed it is 1 by 14 e raised to power 0.9. So for all misclassified point, I have increased the sample weights. And for all correctly classified point, I will decrease the sample weights. Similarly, I will find for all such examples, and then will normalize it. Normalize in next sense, I will sum over all such sample weights to 1. Okay, how will do that? I will just sum over these and just divide every possible values. Okay, now assume you have a different sample weights. So how you will?
Sir, I didn't get the normalization part.
Even I didn't get it such normally.
Yeah, okay.
Sir, and the slides don't have this 1 by n.
That 1 by n is really just 1 by 14 given across, right? So you're initially
for every, so it doesn't make any sense. So even if you doesn't take 1 by n, it's completely fine. Okay, so you can take e raised power minus alpha and e raised power alpha for misclassified point. This is, and for this is for misclassified point. So assume this is your new sample weight. So normalizing means you will sum over all these values should be 1. Okay, let's say new weights are 0.01, 0.05, 0.08, 0.1, something like that. For 4 examples, only 4 examples you have. And how these are your new weights, so how you will normalize those? Sum over these things. You should make sure that this sum comes 1. Okay, so how you will do? Just take the sum and divide it by that sum. Okay, so in that manner, the sum gonna be 1, right? Let's say sum is s, so the s divided by s is so sum over this gonna be 1, right? So this is your new sample weights now.
Okay, sir. Yeah.
Okay, so how you will create the new system now? Any idea how you will create the new system?
So again,
So
we'll
the
have to go
ones-
through each attribute, each feature, and look at which gives you the least entropy. as
Again,
well.
but how you will make use of this sample bits?
The ones with the some maximum sample weights would be taken.
Yeah, so you create a new sample, new training sample. How you will choose? So let's say the new sample let's reduce the size of this data set. Okay, so you have only 4 or 5 data set, and your data new sample bits are let's say 1 by 3, 1 by 4, 1 by 8, 1 by something like this. That's summing over 5, summing over 1. Okay, and then you choose this example in the new training example. You choose this example with this probability. You choose this example with this probability.
So there's some disturbance. I can't hear you.
Is it okay now? Yeah, it should be okay.
Yeah, okay, sir.
Right. Okay. So in the next training data set, you choose this example with this probability, this example with this probability. So in that manner, it makes sense because remember, misclassified points have the higher probabilities because we have increased the sample weight for the misclassified point. So in the new data set, this examples have higher probability of coming again and again multiple times. So we will giving the more importance to that points to train new models. Does it make sense?
No,
so-
sir. Can you repeat? How do we calculate the next term? Now we
for
got this.
creating next system, we will create the new training data set. Okay, for creating new data set, you take these examples with this probability, this example with this probability, this example with this probability.
Okay.
Okay, so it because for misclassified point we have increased the sample weights. This data set has higher chances to appear multiple times in new training data set, right?
Right.
Because we have increased the sample weights for misclassified points. In that manner, we are making sure that the misclassified point will have the higher importance to train the new system, right?
Right, sir.
Right, and those which were classified correctly, we are reducing the importance. In that manner, we are reducing the probabilities of coming multiple times in the new data set and reducing the importance, right? That is the one way. Alternative way is that you can use the same training data set, but using the remember in the defining the green index and all, we use the sample weights. Sample weights as 1 by n for each data set. Rather than using that 1 by n, you can use those sample weights. Okay, so that is again alternative. So any of these two you can choose.
Yeah, the second one was what I think was earlier explained in the lectures also.
So yeah, so earlier that was explained. So alternatively, you can use any of these two.
Right.
Okay. So that's how you create the next system and keep on doing creating the systems depending upon the what error the previous system has made. Okay, remember one thing, always create systems. I mean the decision tree only with one split. Okay. Okay, so any doubts in AdaBoost? Okay, so what is the difference between random forest and AdaBoost? So remember in AdaBoost we grow the full size tree, but in the case of AdaBoost we only create the distance, right? But it's the bagging algorithm is the boosting. So here the procedure or each decision tree can be built independently. It means the learning procedure can go in the parallel. But in the case of AdaBoost, it's a boosting algorithm. So the error of the first systems make influence on the second system. So here the learning procedure goes in iterative manner, one by other, right? And one more, and each decision trees has equal importance in making decision tree, right? Remember, we are taking average or we are taking the majority wins. So each and every estimator has equal importance to making decision. But in the case of AdaBoost, we are giving more importance to those systems which are have higher performance or which has lesser performance. Remember, we are increasing weight E by alpha minus alpha. So if alpha is higher, it means we are giving more importance to that system. And if alpha is less, then we are giving less. Alpha is less, and we are giving less importance to that system to making predictions, right? Because we are not increasing or decreasing the sample base by much if alpha is less, and if alpha is more, then we are giving more importance and less importance to correctly classified. In that sense, we are giving more importance to some systems, less importance to some systems in making decision. Okay, so this is the idea behind this AdaBoost and random forest. So these two algorithms should be you should know in week 10. Okay, random forest and AdaBoost. Next one is gradient boosting. This is again a boosting algorithm. Okay, so I will not go of the mathematical part of this, but I will go to how to create a boosting gradient boost for regression problem. Okay, classification, I will just give the hint how to create. And remember, in AdaBoost, we have only covered the regression problem, right? Sorry, classification problem. For regression, what we do, regression is not covered, but just remember that for misclassification error, and we are finding the misclassification error, and we are taking e raised to power alpha to increasing weight. But in the case of regression, what we do, we set some threshold. Okay, and which crosses this threshold, we increase sample weights for those example, and which has lesser error less than this threshold, then we decrease sample weights for that example. Okay, so you can avoid this part here. It's not important for this. Okay, so again the same thing, boosting algorithm here.
Nitin, why didn't you put the XGBoost over there? XGBoost and gradient boost in the comparison.
XGBoost. Where I put XGBoost?
No, I'm asking. I mean, why comparison is not with the context of this, or is it out of context?
This comparison you are talking about?
Yes.
I'm just comparing these random forest and AdaBoost because yes, sure, they are not comparing because they are pegging and boosting. They should not be compared. But sometimes for designing or building that AdaBoost or random forest, there's some confusion comes in. So that's why I'm just comparing these two.
Okay.
To remember those in better way, you should know the distinction between these two. Okay, let's go to the gradient boosting. Okay, so I will not go to the mathematical part of this. Well, I will go to how to create a gradient boost. Okay, so there are 3 steps. We will start with the root node. In the root node, we make the predictions. What should be the prediction for the root node? Call it average. Remember, average is always the better the random, not the random one, but it's the good prediction. So we will start with the root node. Then we will find the residuals for that, and then we will find that residuals using that predictions. I mean the error, actual minus predictions, and then we'll fit the residuals. Okay, using a decision tree. Okay, let's go to the example. Then these steps will be clear. Okay, so this is the example of Okay, so this is a regression problem where we are trying to predict the weight using the 3 features: height, gender, and age. Okay, so first prediction gonna be average, right? So this is the root predictions, or say base model. I think it is called base model. Okay, so average. So this is the average here. So this is the prediction. So what is gonna be the error here? The residual. So in the next step, we create the residuals, right? So residual is gonna be the actual minus predicted. So 78 minus 67.5. say here 67.5. So every residuals is created now. What is the next step? You fit the residuals. Right. Remember the third step, fit the residuals using a decision tree. And in the decision tree, we restrict the size of the decision tree, generally 8 to 32 leaves. Okay. And then make the predictions again. So what I mean by fitting residuals, for now we'll create the decision tree, but this is not label now. My label is now residuals. Okay. So now we have to create the decision tree. So let's say this is your decision tree. I'm taking only 3 leaves. Generally, 8 to 32 leaves are taken. Okay, so you are taking you are fitting the residuals here. So let's say according to height, and according to age, it has been splitted. Okay, so let's say these two examples comes here. So here prediction is gonna be the average over these two. Okay, so average over these two, whatever that is, and let's say these two examples comes in here. So the prediction here will be the average over these two. Okay, and in this node, average over these two. If these two examples belongs to here. Okay, so now what is gonna be the predictions for the model? It is gonna be the predictions of our first model. What was our first model? The base model. Their prediction was 67.5 plus some learning rate times alpha times predictions here. Okay, so predictions using this model. Let's call it model number 1 M1. Okay, so prediction using M1. Okay, so let's say for I'm to make predictions for this example. So what will be the prediction? 67.5 plus some alpha times, let's say 0.1 time prediction over this thing. So what gonna be predictions here? So this examples comes here and predictions here is, let's say 3.5. So 3.5 here. So 67.5 plus something 0.35. So remember the actual level was 78 and first model was giving prediction 67.5. Now we have better predictions 67.5 plus something, right? Better performance. Okay, so we keep on doing these things again. This is the predictions, right? We will find the residual again. So the 78 was the actual level minus this model is giving this much, let's say 68 point something. It's not good, but just assume this is the predictions. Okay, 78 minus 68.1. So again, you will finding residual for each and every examples. Again, you will do the same thing. You will fit the model, fit the residuals, and create the decision tree. Okay, remember we are fitting the residuals here, not the weights. Okay, and how we are making predictions? Again, same 67.5 plus alpha times predictions using M1 plus alpha times prediction using M2. This is called M2. So for, let's say for first example, 67.5 plus 0.1, 0.35 about the predictions using M1 and 0.1 the prediction using M2. Let's say call this is 0. Let's coming out to be it was 3.5, right? Let's say 5.1. So again, we are getting better and better in that
Yes,
manner.
So this M1, M2 are prediction of residuals, right?
Yeah, prediction of residuals.
So in that leaf, basically the mean of the residuals, whatever is coming.
Yeah.
Okay.
In that leaf. Okay. So that is how a gradient boost model is fit. Keep on doing this thing. Okay. So for classification, for regression, we do this thing. Classification, it is not covered, but generally what to do remember in the case of numeric. In the case of regressions, we have values. So in the classification, rather than fitting the 1, 0 classes, we can fit the log odds. Okay. Again, the same regression kind of problems, right? So rather than fitting the classes, we can fit the log odds in the case of classification problem. But don't worry about these things for classification problem now. So any problem in week 10, you can ask, and then if not, we can start with week 11.
So what kind of questions can come from the week 10? Calculating the boosting process or something, any other mathematical problem?
In week 10, generally mostly question random forest, AdaBoost, and gradient question. These three main algorithms covered. So you won't be asked such typical numerical question, but easy numerical questions. Okay, where you have to find the performance, right? So stump you can create. Stump is nothing but a decision tree, and you know how to create the decision tree. So once you can create the decision tree, you can find the performance because you can find the misclassification error. Such kind of question can be there, or some conceptual question will always be there. Okay, so remember the paper is consist of some numerical question and some logical questions, very conceptual questions.
Okay, thanks, Nitin.
Okay, so can we continue week 11, 12 tomorrow? So I am not available tomorrow. If you want, we can continue on Saturday.
Saturday, I think it will be last day before the exam. So, okay. How much time it will take more?
So 11th week is easy week, right? And 12th week is little, I guess, 30, let's say 40 minutes will be enough for these 2 weeks. 30 to 40 minutes.
Okay, then I think we can continue.
We can continue. Let's take a 5-minute break and then we'll start.
Right.
Okay, so I think this should start now. Okay, so shall we start? Okay, so let's start now. Okay, so what happens in K-means? K-means is unsupervised learning problem. You all know this. because labels are not present. So what our task here? Our task is to group them, right? So our task here is to group them depending upon our problem. Like say let's say you have some different clusters, and you want to know which clusters have same kind, which examples have same kind of features, these features and all. Depending upon that, you try to group them. So how to group them? It's all covered in week 11. Okay, so only one algorithm is covered in week 11, which is called k-means, and k here stands for the number of clusters. Okay, so how many clusters, how many groups we want to define in that distribution. Okay, so so how to do that? So there are some steps to follow. So first, we select the number of clusters. Okay, so k stands for number of clusters. So how many clusters we want to identify the data? So this is your first step. Secondly, you let's say k you have chosen 3. Okay, so you randomly select 3 data points. Okay, and we are calling them centers. On these data points can be from the data set and outside the data set, doesn't matter. Okay, randomly choose 3 data points. Okay, and call them centroids. For each point, you find the distance. For every point, you find the distance of the point from the k centers. For 3, let's say you have 3 centers. For each and every point, you find the distance from these 3 points and assigns every point to the nearest centers. Okay, so that's how you will find the distances and assign to different clusters. And once you have the different cluster, you find the mean of each clusters, and then these means will be the new centroids. Okay, so and then you can repeating the step 3, 4, and 5 until you get the better your clustering stops. Okay, so let's try to understand this. Let's say this is very easy examples. So how many clusters you can think of here in this data set? Let's
3.
call this three clusters. This one, and this one, right? Okay, so let's say I've chosen k equal to 3. So this is my first step. Second step was I randomly choose 3 points. Okay, 3 centroid. So let's say these points, and these points are my centroid. So this is first centroid, second centroid, and third centroid. What is my step 3? I will find the distance of every point. So remember, these centers can be data points or can be outside of the data point as well. Okay, so you will find the distance of every point from these centers. So let's choose this point. I will find the distance from this, and this, which is the minimum. From this is the minimum. Let's call this is cluster 1. This is for this point call cluster 1. For this point call cluster 2, and for this point call cluster 3. This centers. Okay, so first point belongs to cluster 1. What about the second point? We'll find the distance from this point, this centroid, and this centroid, which is minimum. This is minimum, right? So the second point goes to cluster 1. What about third point? You can find the distance from first centroid, second centroid, and third centroid, which is minimum. This is minimum. So the second point goes to cluster second. Similarly, this goes to second, and this point will go to third cluster, right? All this goes to third cluster. Okay, so now these points you have in the first cluster, these points you have in the second cluster, and these points you have in the third clusters. Okay, so what is the next step? You take the mean over clusters. So you will take the mean of these two. Mean means if the data points have the points, let's say this is at 1, this is at 2. So what gonna be mean? 1.5, right? So and what will we mean here? Let's say this is at 3, this is at 4, so 3.5 gonna be the mean here. And let's say these are some points, points on x-axis, and you will take over the mean. So this is now gonna be your new centroids. Okay, you keep on repeating these things. So now, so somewhere here gonna be the new centroid, and this centroid gonna shift here, and this centroid gonna be shift here. Now, so you have these centroids now, these new centroids. Right, so again you will repeat. So for this point you find the distance from here, and from here, and which is minimum. This is minimum. So this goes to cluster 1, this goes to cluster 1, this goes to cluster 2, this goes to cluster 2, this goes to cluster, all this goes to cluster 3, right? And again you will get the same centers, right? Because in the first cluster you have only these points, in the second cluster you have these points, in the third cluster you have the same points. So your clusters are not changing, so you have stopped your algorithm. So when to stop k means And cluster doesn't change. Okay. So can you see the problem here? In this
Yeah,
in
that's randomly selected cluster 2 was not a good selection.
no, we have selected 3 clusters, 1, 2, and 3.
Yeah, so 2 was actually coming within the first cluster only.
Yeah, but
Second centroid.
remember we were saying that in the first cluster, this second cluster, this in third cluster. So why this is happening? We have chosen the right number of cluster. We have chosen 3 number of cluster, and there were 3
The
number of cluster.
centroid is the second centroid is I think more towards cluster 1.
So because we are randomly choosing the clusters, right? Sorry, centroids. We are choosing the randomly cluster. So that randomly initializations is the problem. So how to overcome this thing? So there is only one way. You will find the variation. So you will find the quality of clustering, and quality of clustering is nothing but the variation within the cluster. So in this cluster, you have these points. You find the variation. I mean, you find the distances. Okay, average distances over here, average distances over here, and you will find the average. So that is called the variations over the clusters. So you want that variations to be low, right? Within the cluster, you want less variance, less distances. Okay, so you by finding the variations within the cluster, you access the quality of clustering. Okay, so you randomly initialize again your centroids. Okay, so you randomly start your procedure again, and then keep on doing this for 3 or 4 times you do, or n number times or you do, and you will see for which it is giving the less variations. You will stick to that I mean that clustering. Okay, that grouping. Within the cluster, you take the distances. So first, this is your first cluster. You take the distances within this clusters. Okay, within this cluster and within this clusters. Okay, it's not like you will find the distance of this point from this end for every point. You will find the distance of this point from all those points which belong to this cluster only. That's it. And for this thing, you will find the distances over this thing, from this, and then averaging out. For all such points, you will do that pairwise within the clusters. Okay, not for all the points.
Do we also have to balance the number of samples in each cluster?
Balance means what?
Like suppose the cluster 2 has only 2 points, but cluster 3 has like
no need to worry about it. No need to worry about high variance means you have I mean within the clusters you have well apart data points that we don't want, right? High variance means high distance and they are well within the cluster, they are situated very far, something like that. Okay.
Right.
So you for finding best best cluster, best grouping, you keep on you again start your algorithm, and you do number of times and choose over those n, which giving the best the least variation. Okay, so that's how you overcome this problem. But again, how to choose this k? In this toy example, we can see only 3 clusters are there, but how to choose this k for a training data set where you cannot visualize the data sets? How to determine k? So there are 2 methods for determining k. One is called elbow method. Second is fill out method. So elbow method is easy. So let's look at this. So what you do for elbow methods for different values of k. So k is again, you start with random numbers. Generally, k start with root of number of examples, not root of examples. I'm not sure about this. Please cross check this one. Okay, I'm not sure about this. Okay, so you randomly start k. Okay, you find the variation. Okay, then you will choose another k, you find variations and draw k versus variation. So you will have something like this structure. You have k here, you have variation here. So something like this. So let's say k, you have chosen k something like this. K 3, 4, 5, 6. For this k value, you have found the variations. For 3 is coming like this. For 4 is coming like this. For 5 is coming like this. 6 coming like this. 7 coming like this. Okay. So something like this, you have a structure and you choose the elbow. This elbow you choose. So this is coming to a 5. So I will choose k equal to 5. So this is called elbow method. You will find, you will start with some
What
k
is here
and
in the y-axis?
variation, that distance within the clusters. Okay. I'm not sure about how to choose its k or root n or not. Root n number of.
That's fine. That's fine. This, what is the y-axis? How to derive that y-axis value from?
How to derive? I
how
mean,
to
this is
calculate? After this calculation of the k means, centroid and other things.
okay. So let's take this
Variation.
example. Let's take these examples. Okay,
Yeah.
so once you have grouped them. Okay, using
Okay,
k
fine.
means. Okay,
Yes.
now you have this cluster.
Okay.
Let's
And
do
three clusters.
it here.
Final
Let's
three
do it
clusters
here.
are available.
You have these clusters. You have this clusters and this clusters, right? So this is cluster 1, cluster 2, cluster. This is your final clusters using k equal to something, k equal to 3. Okay. Now you will find the distance here. So you will do pairwise distance between these two. Okay, so that is gonna be your variation within this cluster. You will again do the pairwise distances here and average those out. This is gonna be the variation within this cluster. You will find the variations here. So you will find the distance here, distance here, distance here, distance here, distance here, again distance here, distance here, something like that. Okay, pairwise distances, and then take the average. Okay. And for all these three, you can take average. So let's say coming x1, x2, x3 are the average distances. So you can take x1 plus x2 plus x3 by 3. Okay, so that is going to be a variation. Okay, again, you will start your algorithm with k equal to 2. So here you can see 3 are there. So let's say this becomes 2 clusters at the last by applying k means. Okay.
Okay. The average value is average distance.
Yes, yes. Okay, so you draw the curve between variation and k and choose this elbow. This kind of elbow. Okay. This is the elbow method, but it's generally not preferred because variations is, remember, for if you have high number of features, you have to find distances for every possible pair in the clusters, right? So that distance becomes very, very, I mean, computationally very heavy. Okay, so very complex. Okay, that's why this method is not preferred for high dimension, but the next method, which is Silhouette method, which is generally preferred for high dimensional data set. Okay, so what happens in Silhouette method? We define a score here, which is called Silhouette score or Silhouette coefficient, which is defined as the b minus a upon max of b over a. And remember, this actually Silhouette coefficients gives the idea about cohesion within the same cluster and separation from the nearest cluster. So let's take one example. Here B and A is what? Let's say you have 2 clusters. One cluster is here, and second cluster is here.
So Silhouette method is the most efficient method to choose k.
Yeah, most efficient method to choose k.
Okay.
Okay, so what is B and A? Let's say this point I choose. I'm to find the S for this point. Okay, so what I will do, this is the cluster for this point, and this is the nearest cluster. Let's say you have 3 clusters, one more. Okay, some other. Okay, this is your third cluster. So this is the nearest cluster for this point. So how you will find S? So you will take the A. A is what? The inter-cluster distance. So it is the distances of distance of this point from every possible point in this, every point from this cluster within this cluster. Okay, and you will average this out. So this is your A. And what is B? So B is the inter-cluster distance from the nearest cluster. So this is the nearest cluster for this point. You will take the distances from every point of this point. Okay, these distances and average this out. This is gonna be your B. Okay, so generally you can think as this is your first cluster, this is your second cluster, this is gonna be A, this is gonna be your B, something like that. Okay.
So if you have 3 clusters, then there'll be another B.
No. So what you do for this clusters, every point you find S and then average out to that S. Okay. So for
No,
it may be
A
the
is
case for
clear.
this.
Now B, you've drawn another cluster out there. So I'm taking from that point also that
On
third
an
cluster-
average, I found S for this particular point, right? You will find S for every possible points, every points.
no, A is clear. Intra cluster.
For V, you have to take nearest cluster. That is what.
Nearest
Okay,
cluster, yeah, nearest
okay.
cluster.
Yeah.
Okay, so what you want, B is to be higher than A or A is higher than B? I mean, the greater than B or
So in this
greater than A.
visually nearest cluster is fine. Otherwise, what do you do? Take the distance between the centroids to find which is the nearest cluster.
On an average, it is the same. If you do for every possible point, let's say I'm to find the S for this cluster. So what I will do for every possible points. Okay, I will find S for every possible points and then average it out.
No, sir, I'm asking for B for calculating inter.
No,
How
I'm
will I
asking
know which
for
is the closest cluster? I mean, here
closest
visually,
means, yeah, visually you can do. You can for let's say I'm to find which is the nearest cluster for this point. Okay, so for every possible points within this cluster, cluster you find the nearest points. Let's say for this cluster, this is the nearest point to this, and this is the nearest from this cluster. You will choose which is minimum, something like that.
Okay.
Okay, just the distance measure I'm using to find the distance. Euclidean distance or Manhattan distance. Generally, Euclidean distance is used.
Okay.
Okay.
So
Once I have
taking max of B and A, B is always greater. So why we can divide by
so
B?
yeah, I'm coming to that. Okay, in some case where so and when can S be negative? When B is less than A, right? So it happens only when the clusters are assigned wrongly. So remember this case where, let's say this case. So these are your actually and you have chosen this centroid. So you will come up with this cluster and this cluster, right? So
So
in that case, what will
distance will be always the Euclidean distance, right?
Euclidean distance, yeah. So in that case, S gonna be negative. So S negative means that your clusters are wrongly assigned. So what you want, S is always between -1 to 1. Remember, S negative is very bad clustering, very bad grouping. Okay, or it may be case that your K is very less. Remember, you have 3 data sets, 3 distributions. Let's say something like that. Let me do it. You have, let's say, 3 data points, 3 distributions, something like that. Okay, now you have chosen K2. So K equal to 2, what it will do? It will group to something like that, something like this. Okay, so in this case, B, your S can be negative. Okay, so you don't want S to be negative. If your S is coming out to be negative, what you will do? You will increase the K. Okay, so what S equal to 0 means? What is S equal to 0? I mean B minus A upon max of A. So 0 means positive. So B will be the max. So it will be 0 means B equal to A, right? B equal to means that they are very close. Clusters are very close. So something like that. So cluster are close means they can be of the same clusters. Okay, so the cluster may be of the same type. S0 means. So you want S to be close to 0 or not? You definitely not want S to be negative. You don't want S to be close to 0 as well, because in this case, the clusters may be of the same kind. What you actually want? You want S to be greater 1. So what happens when S equal to 1? In this case, B minus A will equal to B, right? So it means that A is 0. A is 0 means A is tending to 0. It's not always equal, exactly 1, but close to 1. Okay, so in that case, A is tending to 0. It means that your clusters are very well packed and very, or say B is greater than A, right? So, or you can say the nearest cluster is very far. So that is very good grouping, right? If it is S is coming to be close to 1, it makes sure that your clusters are very well packed and maybe the nearest clusters are very well apart. Okay, so you want S to be 1. Okay, so that's how you choose your K. You start some random K, you find the value of S. If it is negative, you keep on increasing K. You 4 different candidates for K, you select the K which is giving the value close to 1. Okay, So that is what I mean by sellout method.
But sir, haven't we increased the computation here? Like we also
Yeah,
need to
competition
calculate-
is again very heavy here. But
But
then
it's-
in higher dimension, this works well.
So computationally, which one is light?
Okay, so in LO method, what we do, we generally find the inter cluster distances, right?
Yeah,
Angle
intra.
variation. Yeah, intra. And here, yeah, the same kind of computation is there. But generally, that sellout method is used in higher dimension. Okay, there may be some other reason, I'm not sure about that. Okay, so this is all about week 11, week 12. Okay, so week 12, I will make use of. Okay, so any doubts in week 11?
So what kind of mathematical, I mean, numerical problems can come from week 11?
What type of numerical? Just okay. So there is only two type of computations, right? Find the centroids. Once you have the data points, you can find the centroids, right? And how the centroids are shifted. Once you have the centroids, how in the next step, how gonna be the step next centroid, right? That you can compute the next centroid.
Okay. What about finding the K?
No, that yeah, you should know how to choose K using LO method and using sellout method. So LO method you should able to draw curve and low. So from looking at the curve, you should able to find which is best K. And if you have been given some values of S for different K, you should able to do which is the best value of K. Okay, some kind of this thing. You should know you should increase K or decrease K, something like that.
Okay. Yeah.
With regard to elbow method, it is clear. What is the elbow point? That is the best case. With respect to silhouette method,
As you want to close to 1. Your S is close to 1.
S is close to 1, that is the best case.
Best K.
Okay.
Okay, so this is all about week 11. Okay, so week 12, I will make use of the slides. That is again true that average distance of the centroid from the nearest cluster, or yeah. Okay, so we have from the okay. Can you see the screen?
Yes.
Okay, so ANL, we are not covered one of these macro bit. I'm skipping this, it's not included. All these things I'm not using. If I'm not covering, you can read it out. It's not a big deal. Okay, so idea beyond what is neural network? Actually, it's taken from the biological neural system. Remember, in the human body, there's neuron system where it connects, where there are different units are connected to each other. There are millions and trillions of such units, and these units are called neurons. So whatever your brain gives you the output, it takes the inputs from the environment, right? Suppose you are seeing some image and your mind gives you that this image is of this thing. Let's say the image of tree. This is the image of tree, or this is so. How it is giving the output? So your neurons is taking inputs from the environment. It is processed, then passed to the different neurons, and it goes to your brain, and that brain is giving the output. So you have a different network. You have a network of neurons, or say connections of neurons, where the inputs is passed from neuron to neuron. It is processed within the neurons, right? So the same kind of network we want to mimic, we want to build, so that we can solve the complex problems. Okay, so that is the idea is taken from biological neuron system. That's why it is called artificial neural network. Okay, so remember, we have to define a network. Okay, so we have such so remember, in the basic unit, basic unit is called artificial neurons, and the neurons is nothing but a logistic model, or say perceptron model. That's it. In what happens in logistic or perceptron, we takes input, we take the weighted sum, and then followed by activation function, right? These different neurons, these different models are connected to each other. This is called artificial neural networks. Okay, so we all in this ANM we have only feed forward. So what I mean by feed forward, input is passed from one layer to another. Layer as connections. Layer are what? Layers are the connections of different neurons. So this is one logistic regression model. This is another. So this is your first layer where we have only inputs. Okay, so this is called input layer. Here, whatever the input is, it is passed to the next neurons in the next neurons. Okay, so that is why it is called feed forward. Okay, feed forward. It means that your inputs are always feed to the next layer. Not, it never goes to the back. Okay, so that's why it is called feed forward networks. Okay, so it can solve both problem regression and classification. These notations should be clear. Data is okay. Okay, this is model. This all things should be clear. I just give you the main idea behind the neural networks. Okay, so I just okay. So can you see the whiteboard?
Yes.
Okay, so I just give you the typical idea of neural networks. You can read it out. So in ANN, what happens? You have different. Let's say you have M features. So M inputs you have, and N examples here. So N inputs means in the input layers you have M neurons. Okay, so these are 1 to M neurons. Okay, these are connected to the first layer. So let's say 2 layers you have. These are called hidden layers. Okay, and 1 you have output layer. So this is called input layer. This is called hidden layers, and this is called output layers. So output layer depend in the number of neurons in the output layer depends upon problem. If you have classification problem, then the K neurons you have. K means number of classes, and for the regression, you have only 1 neurons in the output layer.
The number of output node is independent of number of input, right?
Yeah, number of input. Obviously, for regression, you have only 1 output for one example, right? So you have only 1 neurons in the output. For the classification, you actually predict the probabilities. So for K classes, you probabilities for K classes you predict, right? So you have K neurons for the classification problem in the output layer. Okay.
And
so,
for the hidden layer, there is no constraint.
No constraint for number of neurons. Yeah.
Okay.
Okay, so what happens here? So you have M features, M inputs. So so these M input is passed to the every neuron. So in this neurons, M inputs are passed. Okay, so in this neuron again M inputs are passed, M inputs are passed, M inputs are passed. Okay, so you take the weighted sum of all these inputs. So let's say you have M inputs, so W1 X1 up to WM XM. You have this network plus bias as well, plus B naught. Let's say B naught. Okay, so how many parameters here for this neuron? M, right?
M plus for the bias also you'll have to add.
Yeah, for bias I also so for this neuron again all those inputs are passed here, right? So again M bits should be learned by these neurons, right? M plus 1. Similarly this. So let's say you have L neurons here. So how many bits will be learned by this layer? Each and every neurons are learning M bits, right? M bits, M bits, M bits, M bits. So L neurons will learn M into L bits, right? Plus L biases as well, right? So these number of parameters will be learned by this layer. Okay. So this is the first layer. What is about the second hidden layer? So this neuron will have some output here, some output here, some output here, some output here, right? So these outputs will work as the input for this layer now. So let's say L, if this layer has L and L neurons, L outputs will be here and L outputs will be feed as input to this neurons. L outputs, L inputs to this neurons, L inputs to this neurons. Okay, so let's say you have K, let's say all some other number.
Is it always mandatory to feed all the outputs to a particular node?
Yeah, it's mandatory.
Okay.
Okay, and let's say T. Okay, T number of neurons here. So how many bits will be learned here?
L into T plus T.
L into T plus T, right? Similarly, so each neurons will have one output, right? So each output now feed it to the neurons of the output layer. Okay, so how many? Let's say you have K. K neurons in the output layer. So how many bits will be learned here?
T into K plus K.
Plus K, right? So given in network, you can find the number of parameters which are being learned by this network. Right. So let's say one example you can take. Let's say input you have 10 inputs. Let's say 10 inputs. That's 10 inputs. You have 2 hidden layers and 2 hidden layers with 10 neurons. And your problem is classification problem with 3 classes. So in the output layer, how many neurons will be there? With 2 hidden layers. And each with 10 neurons. Okay, and if you have 3 classification problem, how many neurons will be there in the output layer?
3.
So can you compute the number of biases, number of parameters which are being done by this model? Let's say let's assume not 10. Your first layer has 5 neurons and second layer has 10 neurons. Now can you compute the number of bias?
Yes.
I mean number of parameters. How you will
First,
do that?
10 into 5 plus 5. Then
Yeah, so
add
first, in the
5
first
into
layer, remember you have first layer, all the inputs will be the input feature number of features, right? So every neurons will have 10 parameters, 1 plus 1 bias. So 10 into all the 5 neurons. So 10 into 5 plus 5, right? For the second neurons, how many inputs will be there? Second layer. So these 10 outputs will work as the input here now. So 10, not how many?
5
Okay,
into
so 5.
5
So
into
5. Yeah. So 5 into 10, right? Plus how many bias?
10 bias.
Bias will be 10, right? And for the output layer,
10 into 3 plus 3.
10 into 3 plus 3. So this is gonna be your parameters. So this exercise you should be able to do, and what is there in ANN? So it's just a connections of different perceptron or logistic models. Okay, whatever you call it. Okay, so this you should know. Okay, so all these things are given in the vector form. If you read this all the ideas should be clear. Okay, so
Here
one
also,
notation is
here also the accuracy calculations will be asked.
okay. So remember one thing, for the regression problem, the output layer one has activation as the identity function. Generally, it's not fixed, but generally it has identity function as the activation function. But in the case of classification, it is generally softmax function or sigmoid function. Sigmoid for the binary classification and softmax for the multi-class classification problem. Okay, so let's say you have total L layers. 0 layers denotes the input layer and LF layer denotes the output layer. So how many hidden layers you have? Capital N minus 1 hidden layers, right? Because the 0th layer is the input layer and the LF layer is the output layer. Okay, so that's how you denote the layers. So it means, and S0 denotes the number of inputs in the input layer. S1 denotes the number of neurons in the first hidden layer. SL minus 1 will be number of neurons in the L minus 1 hidden layer. Okay, and SL is what? Number of neurons in the output layer. So it's the regression, then you have 1 neuron, and if it is classification problem, then you have K neurons in the output layer. Okay, so you can just read it out, just understand what these notations are. Okay, so this is your L minus 1 layer, this is your LF layer. So if there are 3 neurons, all the output from this will be input from here. Okay, so input, I mean, so it will be the weighted sum followed by the activation function, right? This is just a perceptron model, perceptron or logistic regression model. Okay. So, okay, one more notation you can understand here. WL denotes the weight vectors which are learned between these two layers. Okay, so let's say this is L minus 1 layer, this is L layer. So all the weights which are learned between these two layers are called are denoted by WL. Okay, so what W11 will denote? Okay, so this column denotes the LF layer and this rows denote the L minus 1 layer. Okay, so which coming from 1 to 1, I mean the output is coming from the first neuron from this layer and which is going to the first neuron of the LF layer. Okay, so this is actually this is W11 X1. So that W11 is denotes the weight vector which is learned from first neuron of the LF minus 1 neuron to the first neuron to the LF layer. Okay, so this is the notations for WL. Okay, so pre-activation is what? Pre-activation is the weighted sum, and activation is the that activation function, and the input to the activation function is the weighted sum of this. So this is called pre-activation function for the LF layer. This is called the activation function for the LF layer. Okay. So it is pre-activation is generally denoted by A. So AL minus 1 denotes the pre-activation for the LF layer. Okay, and ZL is denoted the pre-activation. No.
So your
AL,
mouse is not visible in case you are moving it. So your mouse is not visible. The pen.
because of the slides I'm using.
Yeah.
Okay. So now is it?
Yeah, now it's better.
Okay, so these notations are, if you read these out, these notations will be clear. There's nothing much to cover in this thing. Bake propagation is one thing that I will explain now.
Will this come in the exam? The gradients and all?
Yeah, ANM will come. You will not ask to find the gradient and all, but okay. So even if you don't by heart these notations, it's completely okay. But you should know what's actually happening in a network. Okay, how the weights are learned using gradient descent. That is called back propagation. So what happens in back propagation? You find the total error first. That is called loss function. In loss function, so every derivative using for derivative with respect to every weights and every bias you have to update, right? So you have to find the every weights and every bias, derivative of loss with respect to every weights and every bias. So how you will do that? You will go in the backward direction. I mean, first you will find the weights for the last layer, and then go for the second last, and in that manner you will find the weights vectors. Complete the weight vectors. So let's assume this particular network where you have the last layer is layer 2, then the second last layer 1, and the first layer 0. So here you have weights as W2, okay, and bias as W1. Okay, so what will be the activation function here? Is the just the activation function for and the input for this activation is this weighted sum, right? And the prediction will be what? The output from here. So that is A2. Why it is A2? A2 is the weighted sum which pass through the what is A0, AN?
A2 is correct, sir, because it will be of the previous.
A2
layer.
is the weighted sum. Okay, A2 is the weighted sum. Yeah, okay. And W is the active okay, so what's happening here? A0 means it's the weighted sum which passed through this neuron, and then output will be the activation function of that weighted sum, right? So that is called Z1. Okay, so weighted sum of those. No. So Z1 will be weighted sum of those inputs here. So input here is, remember, it was the weighted sum. So so all whatever the inputs are passed here, it will be weighted. It will be combination will be taken and then passed through a non-activation function. That will be the output from this neuron, and this output will be but now input here. So we will take the weighted sum of this output. So output, remember here it was A1. So we will take the weighted sum of this A1. Right, so this is the input here, and we will pass through the activation function. So this is A2, right? So activation function. So this is the last layer. So the output of here it is A2. So this is your prediction is A2. Okay.
Yeah.
Yes, sir.
Okay. Now you have to find. You have the weights W2, V2. I mean the total parameters W1, V1. Okay, and these parameters you need to learn. Okay, so you will go in the backward direction. So first you will learn W2 and V2. So you will find the derivative with respect to W2 and V2 of the loss function. This is your loss function, sum of squared error. Okay, so first you will find the derivative of with respect to W2 and V2 using the chain rule, because remember it's not L is not directly function of W2, but by hat is a function of A2. A2 is a function of Z2, and Z2 is a function of W2. So we will apply the chain rule to find the derivative of L with respect to W2. Okay, so this you can find del L by del A2, del A by A2 by del Z2, del Z2 by del W2. Remember here. So we are finding the derivative of this with respect to W2. So we'll first find the derivative of this y hat. So y hat is nothing but A2. So we will find the derivative of L with respect to A2, then derivative of A2 with respect to Z2, and then derivative of Z2 with respect to W2. And we will apply the chain rule. In that manner, we will find the derivative of L with respect to Z2. Sorry, W2. Okay, once we have found the derivative of W2, so remember what was del L by del A2. A2 is nothing but by hat, right? By hat. If you replace by hat by A2, what is the derivative here? It is gonna be just A2, remember, right?
A2 minus y.
A2 minus y, right? Or simply you can say by hat minus y. Okay. And what is del A2 by del J2? So remember this equation. This is just A2 is what? G of J2. So you can write in another manner, that is G dash of J2, right? G dash of A2. And what is derivative of Z2 with respect to W2? So remember, Z2 was the linear combination of W2. Z2 was W2
we just A1.
plus V1. So it is just A1. Okay, so that is gonna be your del L by del W2. Okay. Now we have this thing. Okay, this whole thing. This is del L by del. Now we will find the del L by del W1. So in that manner, we are going backward. We are finding with respect to W2 first, then we are going W1 after that. Okay, so that is why it is called back propagation. Now, how you will find del L by del W1? Again, since L is not direct function of W1, but y2 is again a function of W1. Okay, so we will make use of derivative of W2 here. So look at this form. So here L was function of y hat, and y hat are the function of this Z2, and Z2 is a function of A1. So and here A1, Z1 is a function of A0, and A0. I mean that Z1 is a function of A1. So ultimately, for finding derivative of L1, L with respect to W1, you have to find the derivative of L with respect to A1, and the derivative of L with respect to A1 you can find using these equations. Okay, so we will make use of del L by del W2 here to find the derivative of derivative of L with respect to W1. Okay, so we will find the derivative of L with respect to A1 first, and A1 with respect to J1, and J1 with respect to W1. Okay, so what is del L by del A1? So so this was your del so this was your that okay. So similar manner that we have find del L by del W2, similar manner you can find del L by del W1. Sorry, A1, right? Only change will be here. A1 will be replaced by W1, because remember the same manner we can do that for finding del L by del A1. So for finding that, you can first differentiate this. First, you can differentiate this with respect to A2, this with respect to J2, and this with respect to A1. So in that manner, you can find del L by del A1. Once you have that form, this will look something like this. Something like this. This del L by del L1 will look something like this, similar that we have found, right? Okay. Once we have this you can find this. You can find this. This is generally this is just G1 dash, right? G dash Z1. G dash Z1, and this is just A naught, because del Z1 is what? A naught W1. Sorry, W1 A naught plus some bias. So if you differentiate with respect to W1, it is gonna be A0, right? So in that manner, it is back propagation. So is this differentiation or finding gradient that is clear or not?
Yes, sir. Clear.
Okay. So once it is clear, it's all just the vector or metric notations. That's it. If you want to avoid these notations, you can avoid. But you should know what's actually happening to find gradient and all. And updation rule is the same.
In the matrix this vector notation, why do we have dot in the first? No, the previous slide. The previous slide. Yeah, this one. This one in the first equation we have a dot, and the other we have a multiplication. Why is that, sir?
So this dot denotes the element wise multiplications. Element wise multiplication. So remember, this was the that weighted sum, right? So we are doing here the weighted sum. It's not like matrix multiplication. So it is the element wise multiplication. And here it is the weighted sum, not weighted sum. It is that matrix multiplication. Or here it is element wise multiplication.
Okay.
So there's a similar one of raised to -1 also with that dot.
Sorry.
In the next slide, I think. In the next slide, sir. Not this one, the next one. Okay. Yeah, yeah. The y minus y.
Yeah. So this is the element wise product.
And what is the raised one, sir?
What is the dot? Yeah.
-1.
Okay, this dot. This dot I'm not sure about, but what is this AL? This is the output, right? Classification. Regression you make.
-1 is
by
okay,
F
sir.
-1.
But the dot we didn't understand.
I think it shouldn't be here. It's just by into by head minus by head. That's it.
No, it'll be -1 because it's taking the derivative of the log of y.
Taking derivative of what?
Minus y into log of y hat.
So
Okay.
it's the logistic regression part. So it is y log y.
That
When
cross
we-
entropy,
Yeah.
cross
Yes.
that loss, right?
Yeah, and then we take a derivative, so it becomes 1 by y. So probably that's why y raised to -1. But I didn't understand why that dot is given.
Okay, just give me 1 minute.
Sir, is this the Hadamard multiplication that we studied initially? Is that what you're saying when you say element-wise
Yeah.
multiplication?
Yes. Okay, so here it is mentioned. So this is just element-wise product. If M is a matrix of size this is giving the sum of element in the matrix. But what is the raised by at raised power this? Okay, so for timing, I'm not sure about this. I have to confirm it. Then I only can comment on this. But this product, I'm pretty sure this is the element-wise product. But what is this raised to power this?
Maybe it's elemental signs. Keep changing -1 plus.
Okay, so here it is loss. So loss is by head minus y in the case of regression, but in the case of classification, it is gonna be by this is the loss that here it is defined. It should have something this kind of form. This kind of form it should have, right? This is the loss. Okay, I will confirm it and I will I only then I can comment. Otherwise, I'm not able to recognize that. What is that?
Okay, sir, no problem. So you would post it on discourse then if you get a clarity.
Yeah.
And Nitin, where I can find these slides?
Which slides? This is week 12 slides.
No, the slides which you are showing now.
These are the week 12 slides.
Okay.
You on the portal you can find.
Okay. And the previous ones which you used for the revision.
That I prepared for just for this this session only.
Okay.
Okay. So I know because of the time I didn't cover week 12 and week 11 in that manner. But if you have any questions in week 11 and week 12, you can ask on discourse. I will try to answer there.
In ANN, in one of the old questions, it is asked what is the classification accuracy. After passing a classification accuracy, after testing 100 data set points within that the 2-1-1 architecture.
Yeah, I got the questions. So
I've
answered. Yeah, I've answered that on the discourse. Did you check that?
The answer is, I think 0.5 is there, but how to approach is. It is
So
already
did you,
available.
yeah, I answered that on the discourse. Did you check on
Okay.
the discourse?
No, sorry, just.
So go through that thread, and if you still have a confusion on that, then only post on that thread.
Oh, thank you.
So I think we should close the session now. So week 12, week 11, I didn't cover in good manner. So if you have any questions, any doubts in week 11 and week 12, you can post on discourse. I will try to answer there. Otherwise, it should be okay. So all the best, everyone, for your exams.
Thank you, sir.
And thank you for joining.
Thank you, sir.
Close.